Okay, class, we're going to look at transmission of sound to the internal ear. Transmission of sound to the internal ear. So we'll start with this drawing here. Sound comes in and presses on the eardrum, vibrates the eardrum, waves of sound. That then causes the malleus to vibrate, then the incus, then the stapes. Now notice the stapes here is pressing against the oval window. Now the size of the oval window compared to the size of the tympanic membrane is quite a different size. Quite a different size. So what ends up happening because of that size differential, it's about 20 times larger than this. It would be as if a guy and a lady are on a linoleum floor. The guy is wearing a flat heel, the lady a high heel. The guy, let's say, is 200 pounds and the lady is 100 pounds. But because the guy is standing on the floor and spreading his weight out on the flat heel, wider flat heel, he will not damage the linoleum floor as much as the lady who has a spike high heel, because all her weight, even that 100 pounds, is concentrated on one space. So what's my point? My point is that by this size differential between the eardrum and the oval window being about a 20 times difference, then that causes an amplification of the sound. Okay, now from the ossicles, the ear bones, then it presses on the oval window. The oval window is in communication with this scala vestibuli where the perilymph is. So what will happen here is the vibration will move the fluid. Now, fluid cannot be compressed. Gas can. You can compress a gas, which would have been coming out here into the ear, but not fluid. So what will happen each time you push in, this perilymph moves, and then it could go back in the perilymph because they both could communicate with one another in the helicotrema. Then it could go back here into the scala tympani and then go through the oval window. So when you push here, this is going to get pushed. When you push here, oval window, the round window gets pushed. Okay, that's basically what happens. Now, let's get to how the hearing is going to occur. Okay, right here in the scala media, the cochlear duct, what you have are these hair cells along that on the basilar membrane. You have these hair cells. Give me a moment. Okay, here's the scala media. Here's the organ of Corte, spiral organ there. In here, you have these hair cells and you have supporting cells. You have an outer region of hair cells and an inner region. Outer region of hair cells and an inner region we're going to look at. Now, the hair cells right here that you see right here have different lengths. And what the hair cells are, here would be the cell. The hairs are actually stereocilia. Now, a cilia, moves, but a stereocilia does not move. It has to be pushed on. Within the stereocilia, just like the other cilia, just within the stereocilia, you have actin filaments. Actin filaments that's going to make the stereocilia very rigid. And you can see that you have tall ones now and short ones. The taller ones can press into the tectorial membrane. The taller ones can press into the tectorial membrane up here. Okay, so this is the organ of Corti, spiral organ. Here are supporting cells. Here are hair cells. We have outer hair cells and inner hair cells. Outer hair cells and inner hair cells. And it's really the inner hair cells that's going to be the important cells that's going to deal with this hearing. So that's what we're looking at this particular point in time. All right. Now, the way this is going to work is this. Okay, the inner hair cells, which you can't see on this drawing, close to the base of the organ, the cochlear duct, are short and stiff. That's at the base, close to the oval window. As I go down, they get longer and more floppy, longer and more floppy as I go down. Now, everything is going to be based on the intensity of the frequency of vibration, that intensity of the frequency of vibration. Okay, the short, more stubby, rigid ones don't vibrate unless it's a high frequency. Has to be a lot of frequency to make those move. The ones way out here close to Helicotrema are tall and more floppy. So a more low frequency sound could be perceived there. Low frequency sound. Now, each of them, almost like a guitar, have respond to a different frequency. When I say respond, match the frequency of the perilymph fluid vibrating, shall I say. And that matching is called resonance, to resonate, to resonate. So when a sound comes in at a certain frequency, then it will move the perilymph. You'll move the perilymph, and the perilymph will vibrate, which will vibrate right here, along here, which will vibrate that, which is going to be the roof of the cochlear duct, the roof of the cochlear duct. And then when it moves down and a certain vibration matches the ability of the inner cells of the organ of Corti to vibrate because of the vibration of the perilymph or the movement of perilymph, that's where perception will occur at that spot. Now, if the vibratory frequency is too low, below that 20, remember below that 20 hertz, then nowhere will it cause the stereocilia to move. So when that occurs, it'll just go straight out and you will have never perceived the sound because it would be below the audible range based on the frequency. But if it's at any point that it can respond, then it will, rather than go straight out. So that's what you're looking at, is to move those stereocilia. And because of the fact that the frequency determines the pitch, high pitch sounds would be heard at the base, low pitch sounds here at the helicotrema area of the cochlear duct. And if it's too low, you won't have it at all. And if the frequency is too high, that it can't vibrate these up here, then you won't hear it either. Okay? You won't hear it either. So that would mean that when we looked at the drawing before of a cat, dog, and so forth, they would be able to perceive it because they could vibrate at that frequency. All right. So we go further here. So you can see in this drawing here, we're pushing, and the vibration of the perilymph was able to stop here. High frequency closer to the base, medium frequency in the middle, and very low frequency here. And if it can't perceive at all, it would just come around and no perception of sound would occur. So we start with a 20,000, and see here, they would even be more rigid in a dog or cat because they can go above that 20,000. Okay, and an elephant way above there. Okay, so that's what we're looking at there. Now, we go here to this one. So how does all this work? Okay, this is the way it'll all work. What will happen is that on the, when the inner hair cells, right here, that hair is pushed on, vibrates because of the is resonant, matching that vibrational frequency. Then right here at this point is going to be a tip link. This tip link hooks to all of these projections, these stereocilia. All right. When the vibration occurs with these, then it will cause this tip link right here to move because it's pressing against the tectorial membrane. And when that occurs, this movement causes between these cilia the opening of channels to potassium. Now these fingers here, or stereocilia, are in the endolymph. And in the endolymph is a very high potassium, very high in potassium. Okay, so, and there's cations, and then there's also some calcium out there. So what will happen is this. When this pushes, it will open up cation channels. Cations then will enter between here, will go into these areas here, mainly in the shorter ones. And when that occurs, then that positive will bring this to depolarization. You'll raise the resting membrane potential to depolarization. When that occurs, and particularly due to the calcium influx, then that would cause these vesicles to come. The vesicles then would elicit glutamate, the neurotransmitter glutamate, and the glutamate would cause the cochlear branch of the vestibulocochlear nerve to reach threshold, and what would end up happening are action potentials would be carried into the brain. So that's how everything occurs. You'll have to review over it. You'll need to review over it. So sound waves vibrate tympanic, vibrate amplified pressure, cochlear fluid set, pressure moves through the perilymph, as we alluded to. Waves below the threshold hearing travel through the helicotrema. Okay, sounds in hearing range go through the cochlear duct and vibrate that particular area. They can resonate. And that's what we're looking at here. This must have been the area that could resonate. So we come down here. Fibers in the oral window are short and stiff. High frequency, that would be high pitch. Those near the helicotrema, more tall and floppy, lower pitch. This is what we're looking at there, which we already talked about. Here is that tectorial membrane. Here are the outer hair cells and the inner. The inner are the ones that really do the work on what we're talking. That's the major ones. And you see how they're being communicated with. Now, what do the outer ones do? The outer hair cells don't really deal with the sound. So these are afferent. Let me just say it this way, sensory. These are afferent, these inner, sending the action potentials in for the sound interpretation. These here going to this are efferent. And what it appears is that the outer hair cells are important in increasing the responsiveness by amplifying the motion of the basilar membrane. So signals come from the brain into these. And what this does is to increase the sensitivity of the inner hair cells so you can respond better to the frequencies of sound. The other thing we figure that it does is to help protect the inner hair cells from damage, such as when you have loud sounds. Okay, so that's what it appears on that particular aspect. All right, I think that wraps up everything.